Right. Hello, everyone, and we're back for another one of these little maths sessions. The ones we've gone through so far are the more mathsy side of the math skills. I'd like to put out a caveat at the start, actually, on the standard form and decimal form video. Initially, I started writing it as standard form, as you would have come across at GCSE, where standard form is some number expressed as a power of 10. So you do 3.4 times 10 to the 5, for example. And then looking around online at the extremely limited resources available, it seemed that standard form was actually something completely different, which is what I told you it was. And then, having consulted with the textbook, seems to think it is what you learn at GCSE. So I'd say it's extremely ambiguous, because AQA's guidance with the math skills and the implied or indicative mathematical content is extremely vague. I think I wouldn't expect standard form as you've seen it at GCSE to come up, though, because I've not seen it on a paper, and frankly, I think it's higher level than you need. You're not dealing with those kind of numbers, at least on a psychology A-level paper. You might be using it at degree level if you do psychology later on, but certainly not A-level. I can't see you'd get a question where it would be reasonable to ask that of you. So I would assume it is what I told you. But we are going to go on today to do probability and p-values, which is something that people can struggle with, understanding what that number represents. The p is 0.05, but that's something we'll go into. We'll look at type 1 and type 2 errors as well. And there's a fascinating rabbit hole that I'll try and stray myself from diving down today on p-values and psychology as a field more broadly. But let's get on with some p-values. P literally meaning probability value. Simple as that. So AQA says, and as I said at the start in my prelude, the information AQA gives about mathematical content, even on the specification normally, I'm not talking about advanced information, is extremely vague. It doesn't give any concrete examples, just vague suggestions, and literally all they've given for probability is understand simple probability. They don't go into any more detail, so we'll have to make do. But it ties into p-values as well, which is more elaborated on. So we can use decimals to express probabilities. So if you've got a fair coin with heads and tails, the probability that a random coin flip will land heads is 0.5. Of course, you could also express that as a percentage. As we've looked at, you could also express it as a fraction, 1/2, because there's two total outcomes, one of which will occur. But we're looking at decimals, so we're going to say the probability of a coin landing heads is 0.5. Little fun, one of my favorite little facts. I've got a great many of those. If you randomly select 23 people, the probability that 2 of them share the same birthday is 0.507. It's above 50%, which is one of the most counterintuitive things in the world. But yeah, if you're in a class of 23 or more, the chance that 2 people in that room share a birthday is above 0.5, because you would assume it's 23 out of 365, but it's not. It's because you've got to compare every possible pair of people in that room, and you find that you actually get quite high probability. But that's a fun example. But yeah, we can express probabilities as decimals, and it's a very common way to do so. In fact, it's the preferred way to do so in most cases. Probability with p-values works the same way. As I said, probability the P in p-value is P for probability. I need to stop saying probability because I will get my tongue tied. But you'll know from your course that the p-value is typically set at 0.05. It can be set at a lower value, very rarely at a higher value. Could be set lower at 0.01 or 0.001. And if we go to uni, you read academic papers, you'll see that the probability value is typically, there'll be multiple levels of the p-value reported. But what does it actually mean? We've already established on the previous slide that a value of 0.50 means a probability of 50%. So a p-value of 0.05 means a probability of 5%. Well, what does that represent, practically speaking? So it means there's a 5% chance that our results occurred due to chance. So if you took the experiment and you ran the results over and over and over again, where those results were fully random, you would achieve those results that you have obtained in reality by chance 5% of the time. So if you find what you think is a significant result, and you've got a p-value of 0.05, what you're actually saying is we're accepting that there's a 5% chance that these results are just random and they don't actually mean anything. 5% is 0.05 level is quite arbitrary. There isn't a physical material reason it's set at 5%. There is a slightly more abstract one, but it's just the general level of uncertainty psychologists find acceptable. So they accept that going into their experiment, if they accept a p-value of 0.05, there is a 5% chance that if their results look significant, they're actually not. And this creates a huge problem. This is what I alluded to earlier about there is a crisis in psychology. It's called the replication crisis, because if you accept that 5% of studies are going to that have significant results are actually the result of chance, you're accepting that 1 in 20 significant scientific studies are incorrect, and those studies will have been used to inform policy decisions. They'll have been used to inform workplace practices. They'll have been used to inform future research, research funding, drug trials. So when you accept a 5% chance of your results are incorrect, actually that's very generous to that risk. In physics, an acceptable level of significance is, the chance of the results being random is 1 in tens of thousands, 1 in millions. Psychology accepts 1 in 20. So you can make your own minds up about that, whether that's ethical choice, but it is the more imprecise nature of psychology sort of requires a looser definition of what is significant. So there's 2 types of error that can arise from this. I've spoken so far about the first one, a type 1 error, where we incorrectly reject the null hypothesis, a false positive. So we think we've got a significant result and we haven't. That's that 1 in 20 chance. And they are admittedly the most common, because that's what a false positive arises when you have too high a p-value. If your p-value is too high, you're going to get false positives for fun. The opposite end of the spectrum, where your p-value is too stringent, is where you get a type 2 error or a false negative. And in an exam, you would need to refer to these as type 1 and type 2 errors. You can't just refer to them as false positives and false negatives. Do not ask me why. I've got no idea. It's AQA being AQA, but they are type 1 and type 2 errors. They're not false positives and false negatives. That's just to help you conceptualize them a little better. But type 2 errors are false negatives. So where we do have a significant result, but we think we don't. And that usually arises because we've set too stringent a p-value. So we're going a p-value of 0.001, which is used in psychology sometimes. So if you're setting your p-values too strictly, you're going to find your analysis say that you don't have a significant result when actually you may well do. There may well be a real difference happening in your experiment, but you're just probing too deeply to detect it. And that is why we use a p-value of 0.05. It's deemed an acceptable compromise between the risk of a type 1 and a type 2 error. And you could very much get a question like this, where you're given a stimulus and you're asked to explain why the researchers used a p-value of 0.05. And the answer is always, it provides an acceptable compromise between the risk of a type 1 error and a type 2 error occurring in the experiment, so that the researcher is most likely to correctly report the significance of his or her findings. Now, that is pretty much it for p-values probability. You may be told to use an alternative level of significance if you are, if you're doing anything, if you're doing a sign test, for example, you will be told. You don't have to try and second guess whether it's 0.05 or not. Always use 0.05. That is the gold standard. That is the benchmark. I wouldn't actually call it the gold standard based on what I've said, but it is the benchmark. So only use anything other than that if the question requires you to, which it may do, but in academia generally it's not the most common thing to do. To start arbitrarily setting your p-values in other places. I would encourage you to have a read around this because it is a fascinating area. Do have a look at the replication crisis in psychology. There's been huge, widespread attempts, a concerted effort to try and replicate a lot of this research, allegedly significant results from the 20th century, and a lot of them have been found that they don't replicate, that they are incorrect. I think it's called the Psychology Replication Project or something, and it was a direct response to this crisis. There's other issues as well, and this ties into your understanding of peer review and the scientific process. So you'll know there's a publication bias where journals want to. Let me stop sharing my screen. Actually, there's a publication bias where scientific journals, don't want to publish negative results or null results, rather. They only want to publish significant results. And as a result of that, tying into p-values, a lot of psychological and scientific researchers broadly do what's called p-hacking. And it's a term you may have heard that's slowly seeped into public consciousness. But it's where scientists will, an example I always use is caffeine and memory. So scientists will be looking at the relationship between caffeine and memory. They will find no result, but the scientist needs to get a positive result to get this study published. So they'll say, okay, I'll look at the effect of gender on caffeine and memory. And then so they'll split their pool of data into males and females, and they'll see that, well, actually there's still no difference. Men's memory scores don't respond to caffeine any differently than women's memory scores respond to caffeine. So then they'll start to look at age and say, well, what about 18 to 24s? People love coffee, love energy drinks. There's going to be a difference there. They've been immunized against caffeine in some way. Compare them to older people. They still find no difference. So then they start bringing in other factors like ethnicity or geographical location, socioeconomic status. And remember, I said when you set a p-value of 0.95, you accept a 1 in 20 chance that your results are going to incorrectly come out as significant. Well, every time you go through this process of adding a new variable to see if there's a significant result, you're increasing your chance of this happening. You're increasing the risk exponentially for false positive every time you go and add something new. Because the first phase, you're just looking at gender. Then you're looking at, so you've got 2 variables there. Then you could be looking at 4 age groups. So you've got 4 age groups of men, 4 age groups of women. You've got 8 now. But you only need to get to 20 before you're almost dead certain to have a false positive. So it does tie into this p-value business, does tie into peer review and scientific process as well. But I have already rambled long enough, so we will call it there. That'll be the end of today's session, or whenever you decide to read it. I suppose it's always today, isn't it, somewhere? So thank you for watching. Hope your revision is going well, and I'll see you very soon, probably for some more math skills, more graphical content, perhaps, maybe some biopsychology. We'll see how I feel. But until the next one.